Okay, so now we know about states, how to represent it, so how to represent them. So how do we represent the process? So again, let's just draw our VP representation here. Yes, like that. So here is volume and here is pressure. And let's suppose I'm starting on some state A down there. Okay, so this is A. Now imagine the following. Let's just have this expansive system that I showed you before. So it's like this. For this example, actually, it's not very important, but I just want to be accurate. So for this example, let's just assume that this is insulated adiabatically like that. So there is like a double layer with a perfect insulator. And I have my system with certain volume, V, and it's in equilibrium, so there is a pressure which is homogeneous throughout, volume is VA, and there is a pressure that I will call PA, and a temperature that I get from the equation of state TA. And everything is homogeneous and nice and equilibrated. It doesn't look very homogeneous, so let's make it more homogeneous. Okay, good. Well, not so much, but anyway. You are there, and now the experiment that I propose you is that you do a quench, okay? So you very fast change the volume from the initial value to some final value which is larger, which is here, VB, and this was PA. So what happens to the system? Well, initially nothing happens, right? The instant after you have made this sudden motion of the piston, the gas hasn't realized anything has happened. The density of the gas in this side is still constant and the same it used to be before. The pressure is still PA here, but what happens is that the pressure in this side is zero, and the gas will soon realize that there is a void here, there is vacuum, and it will want to expand against vacuum. And then gradients of pressure will occur, gradients of density, complicated turbulent motion probably of the gas, and so on and so forth. So we know that when this is happening during the transient dynamics, the state of equilibrium of the system is not defined. The system is out of equilibrium, okay? And only asymptotically, at very long times, the pressure and the density will become homogeneous and constant throughout, and then we can talk about a temperature as well. Okay, so when pressure is defined, we can start talking about temperature. So there will be some temperature TB, pressure PB. Say the pressure PB is somewhere here, yes, like there. So the final state of equilibrium of the system is P. But what happens in between is something we cannot represent in the VP representation, because in the VP representation, so whenever you have thermodynamic variables here, they are only defined in equilibrium. Out of equilibrium, they have no value. It's not that they have an intermediate value that is changing over time. They simply are not defined at all, okay? So if you want to somehow represent the process that takes place between A and B, you can draw, if you like, some discontinuous wobbly line like this. But really, it's not legitimate to even plot such non-reversible process. Some such non-equilibrium process. So okay, then let's do a slightly different thing. So let's go back to BA, PA, and TA in equilibrium. That's not what I wanted to do. There you go, and there you go. So we move the piston back to its original position around here, and we have the homogeneous gas. And now instead of changing the volume from VA to VB, we just open up the piston a little tiny bit. Okay, so now our volume is V8 plus delta V. Again, the same thing happens. The system is temporarily out of equilibrium. There will be some transient dynamics, and the system will re-equilibrate and define a new value of pressure, a new value of temperature. And this pressure, what happens is that because I just did a tiny change in my system, it's going to be closer to the original one. Yes, and then I can continue doing the same thing. Okay, and again, if you want to really feel like you want to represent the process graphically, you do some sort of discontinuous line like this. And if you continue to do such little incremental changes of the volume in this adiabatically insulated system, well, you will find intermediate equilibrium states that are there, and there. What happens now if you make these increments really differential? Okay, so really infinitesimal. So what happens is that you will get a continuous succession of points in the VP representation, and they will connect the initial state with the final state. And this line here is a process, okay, while the endpoints are states. This is not just any process, this is a quasi-static process. Quasi-static process is a process in which each of the individual states that the system is in is a state of thermodynamic equilibrium, okay? And this kind of processes, just like a perfectly insulating or adiabatic boundary, are just an idealization, but they are very useful idealization. And most of thermodynamics that we are going to see is going to be about quasi-static processes, okay? Now let me just make a distinction between quasi-static and reversible. So first of all, what is a reversible process? So reversible process is any process that can be reversed. Okay, so it's as simple as that. So you know that when you have a system, when it's not insulated, it is, imagine, in contact with other systems. You have one system, sigma 1, and then you have another system, sigma 2, and they maybe are interacting with one another. It could be mechanically, maybe there is a piston that can move this way or that way between them, maybe there is also heat exchange, whatever it is. When I say a process is reversible, I mean I do something to my systems and I go from one initial state to a final state quasi-statically, okay? And a process, I would call it reversible if when I repeat the process in reverse, so I undo whatever it is that I did exactly in the same way, but playing the movie backwards, then the state sigma 1 and sigma 2 and any other states that are in contact are restored exactly to their initial state that they had before. If anything changes when I close the cycle, then it is not a reversible process. It could be a cyclic process, it could be a quasi-static process, but it's not reversible. Okay? So system and its environment and any other system in contact with it should go back to where they were in the beginning. Otherwise, it's not reversible. But for sure, all reversible processes are necessarily quasi-static. Okay? Now, almost all quasi-static processes, I will concede that to you, almost all quasi-static processes are reversible, but not all reversible forget that. Almost all quasi-static processes are reversible, but not all of them. There are some quasi-static processes which are irreversible. One example of them, okay, so imagine that you have a system that for instance, this piston, okay, so you are moving the piston extremely slowly so that the time scale at which the position of the piston changes significantly, it's much larger than the time it takes the system to reach equilibrium, a state which is sufficiently homogeneous that for all practical purposes I can consider it to be of equilibrium. So that process, yes, sure, it will be quasi-static, but in real life this piston is not going to move without friction. So there always will be some frictional forces proportional to the velocity. Even if the velocity is tiny, that I'm moving this piston outwards, it will be finite. And this means that because of the friction, I will be dissipating heat away, okay? So something will be heated up due to this dissipative work that I'm doing. I haven't defined work yet, but you know work from mechanics. So I'm making some friction, this friction dissipates heat away. So imagine I go all the way down to volume B, and then I want to push the piston back. So I know that the system has gone from state A to state B, and let's say the environment somehow must have absorbed this heat that I'm releasing as a result of the friction. And then I have to push my piston back. I told you I want to reverse the process. I went from A to B, and now I want to see if I go back to A, if everything remains the same that it was. So of course, while I'm expanding the system, yes, well, okay, in this case, it's I told you that these walls were thermally insulating, so forget that. The point is that the piston will go back to its original position, yes, then the pressure and the temperature of the system will again become exactly the same thing they were before, PA and TA, but the environment will not release or surrender all the heat it absorbed during the expansion due to the friction, but actually will receive even more heat, because when I push the piston in the other direction, friction is again being made and more heat is being dissipated into the environment. So in this case, you can argue, okay, the environment here is receiving heat overall when I close the cycle. So the environment is not the same as if it was in the beginning. Okay, so that process is not reversible. Of course, you could argue, okay, but this is a really picky thing because, and it is, because if you are truly quasi-static, then this velocity is going to be zero. Yes, so it really tends to zero. So if the velocity tends to zero, any frictional force is also going to go to zero. So this heat that is released is going to go to zero, and then in the quasi-static limit, things are reversible in this example. Okay, you have a point there. Now I can show you, and we will see that later in this course, an example of a process which is quasi-static, truly, ideally quasi-static, and it's irreversible. Okay, so we will see that it is true that this is an example where other things happen, change of phase from gas to liquid, but it is an example of a quasi-static process, truly quasi-static process, which is non-reversible. So always keep in mind the meaning of reversible and the meaning of quasi-static.